Good morning. So it's lecture number 6. Today's lecture clearly is the most important lecture in this entire course. And we're going to go slowly today. So we're going to slowly look at the different matters that really makes a major difference in terms of how to describe the flexibility. And today we're going to summarize a little bit about the most important matters of the finite element method. And also I'm hoping that there's going to be if everything goes correctly, a total of 5 in-class quizzes. So today is pretty much, well, heavily occupied by in-class quizzes as well. So uh, if everything goes as planned. So then once we summarize everything related to, most important matters related to finite element method, then we're gonna move on and look a little bit about the modal reduction technique. And in the description of modal reduction technique, we need to take a look about eigenvalue analysis. And eigenvalue analysis is something that takes us in turn very close to mechanical vibrations. And we can also look like how is that we can change our set of unknowns to another space. So in finite element method, the space we are solving is this nodal degrees of freedom. So in a static finite element method, this is how the static equilibrium look like. So I have here a stiffness matrix, and then I have here externally applied forces. Stiffness matrix multiplied by displacement. So this guy here is a displacement, is elastic forces. So elastic forces equal then external applied forces. That's what this equation essentially is telling us. Now what we wanted to do in the finite element method is that we wanted to solve the nodal degrees of freedom by inverting the stiffness matrix and then multiplying that by vector of external applied forces. And now what we're going to do today is we will move from nodal degrees of freedom to another space of unknowns. And this another space of unknowns is called modal coordinates. So what from nodal degrees of freedom, we're going to move on to something that is called modal degrees of freedom. This is going to be very important. And for sure, this will be something that I will ask in the midterm exam. So that what follows today. And you see, what follows after that is that then there's one more week about the modal reduction techniques and then the summary, and that's about it. So we are 2 weeks away from midterm exam. So things getting hot in that perspective. So make sure you're following this lecture number of times before you're entering the midterm exam. And the instructions regarding how the midterm exam will be conducted, that will be offered to you next week, Monday. So this week and next week, Monday, those are the 2 weeks that is very important you to follow what's going on. Okay, but with that, I say that let's first summarize what is the deal with the finite element method. And the finite element method, okay, this is my kind of like biased opinion, but in my opinion, finite element method is all about kinematics. How is that we're describing the particles to behave between the nodal locations? So this is something that is very kind of like an essence of the finite element method. So in the finite elements, again, let me get started from the little bit bigger picture. So the finite element method, what we're gonna do is that we're gonna discretize our structure to small elements. Okay, let's say that we have a beam structure like this, and the beam structure is connected to ground, so there's a boundary condition like this, and then there is a force applying to this structure like this. So what we're going to do in finite element method is that we're going to discretize this problem to small pieces. These small pieces are called elements, and elements are connected together in nodal points. Nodal points has a certain number of nodal degrees of freedom. And if we're going to take an example of, well, very simple beam element, so we're going to take a look about the one element here. So the one element here consists of two nodes. Each of these nodes has a displacement in a transverse direction, and they also have a rotational degrees of freedom. So this element here have a total of 4 degrees of freedom. A total of 4 degrees of freedom. Then what's also important is that one nodal location has 2 degrees of freedom. And again, these 2 degrees of freedom is a displacement in a transverse direction and rotation. Now, because the entire element consists of 4 degrees of freedom, we can describe particles between these 2 nodal locations by using polynomial expansion. Now, you may wonder, like, why polynomial? So why don't we just use a, let's say, a trigonometric function? Well, you could use that. And we're going to discuss later in this course that there are alternatives for polynomials. We could use also NURBS, which is this one here. Let me spell it to you. NURBS. Non-rational, non-uniform rational B-splines. So that's one option. So we can use something like that as well. And that's something that is a kind of like drawing objects used heavily in CAD software. So we could use something a bit different as well. B-splines. So yeah, so non-uniform rational B-splines. So that's one option. You could use a trigonometric functions as well. So that's possible. But polynomials are most frequently used because they are mathematically very pleasant. What makes them so pleasant mathematically? Well, what you need to do with your safe functions is that you need to differentiate that your safe functions with respect to different coordinates. And polynomials are so easy to handle that kind of operations. So they are easy, mathematically easy to deal with. So that's why, shortly speaking, polynomials are used. We could use a polynomials all the way. So what we could do in finite Selman method is that we could use these polynomial coefficients as unknowns, but they're a little bit unpleasant to use because they don't have a clear physical interpretation. So that's why we're converting expression of pure polynomials such that the number of the degrees of freedom is expressed by using nodal degrees of freedom. So we're going to do this conversion. And in this conversion, or when we do this conversion, we get safe functions. Safe functions are telling how is assumed displacement when each of these 4 degrees of freedom are activated. So when there is a displacement to each of these 4 degrees of freedom of the element, how is it we can assume particles to behave between these nodal locations? This is super important. And this is how they behave if you're selecting the polynomial like it is shown here. So if you have a displacement in your first node here in a transverse direction, this is how the polynomials are assumed, the particles are assumed to change their position. I think there was a little bit of break, and that was simply because my headset, that too is connected to that is connected to my computer and my mobile phone, and somebody just tried to call me. All right, so I was here to explain what happens if you have a displacement in the first node, transverse direction. So this is how your particles are assumed to deform. All right. So what about the rotation in the first node? This is how your particles are assumed to deform. So they're telling how they are relatively moving with respect to each other. How much they do this kind of motion? Well, this you don't know that time because this will be then defined by how is your nodal degrees of freedom. So once you know your nodal degrees of freedom, which remember what that was the one that you're solving in your finite element problem. So once you're solving this guy here, then you know your nodal degrees of freedom. And then you know eventually how is your deformation of entire structure, not just the nodal location, but every single particle in your system. All right, so then here are the polynomials in another end of the beam. So this is how they look like. And soon, remember, very soon there is going to be in-class quiz about nature of safe functions. So you may log in yourself to in-class, the Socrative already, and you can see that the question is the physical interpretation of safe functions, and then there's 4 options. Okay, right. So what if we are not happy with this polynomial expansion, but we wanted to do something a little different? Yeah, we are allowed to do that. How this will affect to us then? Well, it will affect in a way that the particles between the nodal location will have a different assumed deformation. So they're going to have a different kind of displacement. So which one is the best better? Well, that's hard to tell. This is really hard to tell. And it's a question that is actually very complex to answer. And there's no clear solution to that. Sometimes, however, when you're selecting polynomials not in an order, but a little bit like random way, you get the non-confirmed elements, and these non-confirming elements sometimes have a faster convergence rate than the one that the polynomials are selected in a row or in an order that they appears in Pascal's triangle. So this is how is a safe functions if you're changing the polynomials to be like this. Again, you just have a slightly different assumption. How is a soul of the element? How is the inner life of the element? And this is how they look when you're comparing them. And you can see, there are clear differences. So this is the one that is based highest of third order polynomial. This is a fifth order polynomial, and they look a little bit different. But which is a better? Well, that really depends on your problem. And remember, this is just a piece of solution. It's just a piece of solution. You keep on adding these solutions, and you're able to solve the entire problem. So that's how it goes. That's the idea. Let's say kinematics of finite element method. Once you have the kinematics, it's almost the same like in the multi-body system dynamics. So once you have a kinematics ready, then creating the stiffness matrix, mass matrix, everything like that is very simple. So it's just a simply very mechanical work, which is based on your kinematics. So kinematics is the one that you can only change. And once you have changed that, or once you have set the kinematics, then you just do the mechanical operations and that's it. You end up to have your stiffness matrix, your mass matrix if you're looking at the dynamics. Okay. One of the things that is not mentioned in my slides, and I think that I need to mention that in my summary slides, is that finite element model behaves or is structured in a very different way comparing the multi-body models. Remember that in the multi-body models that the unknowns, which were called generalized coordinates, they were not overlapping. So regardless how you do the connection based on the joints, that never changed the set of generalized coordinates. In the finite element method, that behaves a slightly different way. Because in the finite element method, so if you have here the first element, second element, and the third element, and you think about the stiffness matrix of the first element, so let's put it like this, so it's a beam element, so it's a 4x4 stiffness matrix. This is then overlapping when you're constructing the stiffness matrix of entire structure. There will be actually 2x2 area here, which is overlapping between the the element number 1 and number 2. And the same here, so number 2 and 4, there's going to be this 2x2 area which is overlapping. So there's a pretty much overlapping, a lot of overlapping in your construction of your entire stiffness matrix. We will take a look at that in a bit later today, shortly, but there will be also a more thorough explanation about this next week when we are preparing ourselves to midterm exam. And now, my first in-class quiz of the day, and I see I have 13 viewers this morning. So let's see how well we do. Is this? physical interpretation of safe functions. Show the way that an element can deform. Defines the rotation of a particle. Let me repeat. Defines the rotation of a particle. Okay. Defines strain displacement relationship. And the final option is that no clear interpretation. One only is correct. So shoot it. And the game is on. So what's going to be the success rate? Two competitions here. So what's going to be the success rate? Well, yeah, I don't want to do this other competition, just the one competition. So success rate competition, and that's it. And I see that already I got 4 answers. Oh, okay, so now it's getting started from the 100%. We'll see that. Yeah, the other competition that I wanted to set, which is not the official one, is that what's going to be the percentage of the option number B? How many people will vote the option number B? But I will not do that. So that's not the game. So the only game we have at the moment is how is success rate. Okay. I got 8 answers, so I guess that there's still a bit more to go. Okay, 10 answers. 11, and when I look at now the number of viewers is 13. So my personal guess is this: 100. So that's me. Okay, so 11 answers. So I guess I'm gonna just wait a couple more seconds, and then I will go. 13. I guess. Oh, 14. 14 is now. I guess this is it. So success rate today, and this is not easy. I need to admit that. This is a little difficult because what is really the role of safe functions? What is a physical interpretation of safe functions? What is that they doing for you? It's not at all simple thing. But what they do for you is that they define the way that the element can deform. They directly are not telling anything about the strain. Oh man, look at that. You know, the different. So what is this? Oh my God, I can see that my, I have a bit mix up here. You know, the way I have set this in-class quiz in my Socrative is different than it reads in my slide. Because look at this. Where is it? You know, this is how it is in my slides. So the option number B is define the rotation of a particle. And here it defines the connection between the neighboring elements. Sorry about that. Anyways, that too is incorrect. So it's not really related to that. And let me go back here. So defines the rotation of the particle. Remember, that's very incorrect because, again, particles do not have these rotational degrees of freedom. Define the displacement, strain displacement relationship. No, that's not really the case because later we're going to learn that there is it's like how is it you can define the element behavior. That's the one that defines the strain displacement relationship. But it definitely shows you the way that an element can deform. Okay. Yep. So it's a good old particle rotation. So it's back in a play. So I'm very happy that too. So I'm just sorry that I missed this. I made the mixture about how the in-class quiz was shown in my slides and in Socrates. Sorry about that. But it's always a lot of fun. It always keeps me happy. Rotation of particle keeps me happy. Joy of the life. Okay. So with that, so let's move on. There's going to be another in-class quiz momentarily. So stay tuned. All right. Now, remember why we do this whole business. Why we do that, because we are more about how is it we can describe the deformable bodies in multi-body framework. Well, in a multi-body framework, if this is what we're interested in, we wanted to then describe this vector u bar f. So that's what we are after. So vector u bar f, which for sake of simplicity here, is just denoted as a vector u. So it's not the bar, but this is still with respect to body reference coordinate system. So that reference coordinate system here. So if you wanted to solve this vector u bar, how you can do that? Well, you could create a finite element model. You can introduce inertial forces, elastic forces, externally applied forces, and with using those 4 different kind of forces, you can solve the acceleration of your nodal displacement. And like we discussed shortly a week ago, this is not the way to go. Why? Because reference motion, this large translation and rotation, is described by using 6 or 7 coordinates, depending how you describe your rotational parameters. But let's just say that we're using them, we're describing the large reference motion by using 6 coordinates. So 6 coordinates. And then a typical finite element model consists of easily 10,000 degrees of freedom. Why? Because people want to play safe. So they want to use a fine mesh, meaning that they use a lot of elements. Why? Because remember, the finite element solution gets better and better when you're increasing the number of these piecewise solutions. Now, you don't necessarily need that much, but typically it's I can see that there's a trend that people are a little bit overshooting what comes to the number of elements. They just want to play safe. Let's put it this way. And that's okay, because usually if you're solving a static problem, you do have enough computer power to solve it. So it's not a big problem to make very fine finite element mesh. Usually there's no serious drawbacks other than the computational efficiency associated to high number of finite elements. There is something that is more theoretical, like something like there is a possibility that there is a numerical difficulties, but I don't think we need to discuss about that, because you eventually going to use a commercial finite element software, and they are all tackled. These kind of problems are tackled in a commercial finite element method. But I was here to explain that, this mass matrix can easily be size of 10,000 times 10,000. Of course, they are not like really a matrix which having this kind of this many components, but they're using sparse structure in the programming, which helps a little bit. But still, roughly speaking, you can put an image in your head that there's a 6 versus 10 times. 6 versus 10,000. And things are not matching. So we need to do something to this number. So we need to reduce this number to make it roughly in the same neighborhood that the reference motion is described. Roughly in the same neighborhood. Doesn't need to be 6, but let's say that need to be less than 100. It would be nice if it would be less than 100. All right, so what we can do then? Well, we could do this trick that I shortly mentioned to you a week ago. So we can move from nodal degrees of freedom to modal degrees of freedom. Now this is easy to say, but really needs a major effort to understand like what this means. What is this thing? And soon I'm gonna try to explain this to you by using a drawing. All right. Now the beauty of this method is that if you can do this mapping in a way that if this is your original set of unknowns, let's say again this is this 10,000 number of unknowns, you can move to 10,000 number of modal coordinates, but then you don't reduce the problem. But you could reduce the problem, and instead of using 10,000, you could possibly use just 100. So you can go down from 10,000 to 100. Yes, you will lose certain number of, you will lose accuracy, but not so significant you may think that it will lose the accuracy, but definitely it will boost the computational efficiency a lot. Because think about 10,000 unknowns and then you go down to the 100. That's a huge, huge difference. How you do that, that's what we're going to discuss next. All right, and then here are the questions. I think that I mentioned these already to you, so no need to repeat them this time. But here is a structure that I would like to look at that this time to explain what is the deal with these nodal and modal coordinates. Now here's what I recommend. So if you are middle of the Netflix movie or something in your while you're following this lecture, or you even if you're looking the Winter Olympics, put them aside because this is something that is a fundamental and very critical to pass this class. Okay. What I have here is a cantilever beam. And the cantilever structure here is modeled by using 1, 2, 3, 4, 5 elements. Okay, so 5 elements, and I have here 1, 2, 3, 4, 5, 6 nodal locations. Sorry that I'm blocking of you a little bit. Yeah, I can see by the way that my picture is a bit bigger than it was or usually is. So let me make myself a bit smaller. Here. All right. Okay. All right. So I have six nodal coordinates, or excuse me, not the nodal coordinate, but 6 nodal locations. Now let's think about that. Each of these 6 nodal coordinates, they have 2 degrees of freedom. So this would be a 12 degrees of freedom system in total. Now this first node is actually attached to ground. So there will be boundary condition that will take a 2 degrees of freedom away. So what will be left is a 10 nodal degrees of freedom. All right, so that's the setup here. So what we're doing then, when we, let me take this, let me make this clean again. Okay, so when we're imposing this external applied force to this structure, which is again the structure that consists of 5 elements, 10 degrees of freedom. So I have here a force. What I will do is that I will create this stiffness matrix that describe each of these 5 beam elements. Then my vector of unknowns, nodal displacement, and my vector of external applied forces. Okay, we're going to take a look at the details a bit later. But just keep in mind that this is a big picture now. Okay, so we will solve this guy here by inverting the stiffness matrix and multiplying vector of external applied forces with that. Okay, so what we're going to get then? So we're going to get the vector of 10 units. And this vector will tell how is each of these nodal location, how is it they are having the displacement in the y direction and how much they have rotated. All right. So let's say that this is a final solution. So this is how we were able to solve it. This is because of the force applying here. Now, what we could do here is that instead of using these 10 displacement or 10 unknowns to solve this problem, I could look at the way this structure can deform, the way this structure can deform. So we can look at kind of looking at what are the nature of the structure, what are the feature of the structure. And the easiest way to do that is that I can conduct an eigenvalue analysis. And in eigenvalue analysis, I'm looking at what the heck? YouTube is not receiving enough video to maintain the smooth streaming. I guess it is okay. I guess it is still okay. All right. So let me take this away. So this was this kind of like conventional nodal degrees of freedom way to do it. But what I could do then is that I can look at the feature of the structure. Oh, I see. Okay, I think now it's an excellent connection. It was somehow related to my camera. Again, good news, by the way. I purchased a new laptop. I don't have it yet, but it's underway to my office. And as soon as it comes, then the YouTube will be in another, YouTube streaming will be another level. No technical mistakes. No problem in my camera anymore. And I heard that it's going to be in my office after a couple of weeks. All right. So what I could do is that I could look at the features of the structure. And I could think about, if this would be a system of, vibrating system, how this will vibrate. What are the vibrations of the structure? Well, the lowest possible vibration, I think, or the way the vibration can happen would be like this. This kind of like simple deformation. Pretty much what was the solution of the problem when we solve it in this way. But this will be now an eigenvalue problem. So this is the way structure can deform. Way means that there is a certain way that these nodal displacement can move with respect to each other. All right. How much it can move in this way? I don't know. I don't know. Let's just call that this is a way. Well, let me use a little bit of different notation. So this is a, uh, let's put it like this. No, let me make it clear. Let me take it off. Let's just call it like, okay, like mode like this. This deformation mode, which is a vector here. This is a vector that tells how is a relative displacement between the nodal coordinates. So way the structure can move. All right. How much it can move this way. So this is a numerical vector that tells relative displacement of these 10 nodal coordinates. How much it will move like this? I don't know. I don't know. So let's multiply that by question mark. So that's question mark is going to be my modal coordinates. Now, if my system initially consists of 10 degrees of freedom, 10 nodal degrees of freedom, this is a 10 here, I'm able to see 10 different ways that the structure can move. So this was the first way, associated with the lowest frequency. Second way would be probably something like this. Again, I don't know how much this structure will move like this. I only know the way that it can move like this. It can move like this. Okay, let's call that as a way number 2. How much it's going to move in a way number 2? I don't know. So let's multiply that by question mark number 2. And this is how I can continue. I can look at the 10 different ways the structure can move. And probably the 10th way that it can move will be something like this. I don't know that by heart, but I'm guessing that it's going to be something like that. So that's going to be my 10th way that it can move. How much it's going to move like this? This is going to be my 10th question mark. And now comes something very important. Some of these ways are not important. And because they are not necessarily important, I can ignore some of these ways. And that's going to be the modal reduction technique. Now, let's go back to this. Remember what was mentioned in 2 slides back. So was this U equal to modal matrix multiplied by modal degrees of freedom. That was mentioned there. What this means. So if I have here 10 nodal degrees of freedom, I can have 10 ways that the structure can move, and these 10 ways are described by this matrix here. It just numerically tells what are the ways that the structure can move. And this is then telling how much each of these modes or a possible way to deform are contributing in a final deformation. So that's my question mark. So now here in my presentation, P and a question mark are the same thing. Now, as was mentioned also in my slide, what I can do then is that I can use not the all modal coordinates, but some of them. And I will get an approximate solution by such the way that I will take now here too, this is this guy here. So I can take my first modal, or first way that structure can deform multiplied by first modal coordinates. I can take my second multiplied by modal coordinates, and maybe the fifth, and I will get an approximate that is okay. It's not exactly same where I started, but I don't sacrifice that much about the accuracy, but I will gain a lot in terms of computational efficiency. So if this is a fifth that I'm taking, this is how it's going to be. This is fifth as well. Okay, so let's take a look. I don't know if you guys were able to follow my explanation. Let me summarize this shortly. Here. Okay, let me take up all these drawings away. Okay, now, conventional way to solve this static problem would be to solve this equation. And in this equation, this nodal decrease of freedom will be associated to each of these nodal locations. And each of these nodal locations has 2 degrees of freedom. This one here is connected to ground, so I can ignore that. So it's going to be 5 nodal locations. Each of these nodal locations has a 2 degrees of freedom. So that's going to be a total of vector of 10 unknowns, which is okay. So it's not a huge problem, but just to demonstrate what, how you do this modal reduction. Okay. Now, I don't want to use these nodal coordinates, but I would like to take the look at the entire structure. And I would like to find the ways how the entire structure can deform. How can I find those? Well, I can actually find it in many different ways, but maybe the easiest here is to conduct an eigenvalue analysis and looking at what are the vibration modes. Well, I'm gonna explain this vibration modes concept to you momentarily. So what are the vibration modes and associated frequencies? But let's just look at the vibration modes. So if you would, let's say that if you would have these force as a function of time, and it would be a like sine function like this. You keep on increasing or changing this frequency here. How would be this deform? Probably the first resonance will be something like this. Having the resonance like this will be the way the structure can deform. Okay. Second would be something like this. Not a great drawing, but you get an idea. Third will be something like this, and so on and so forth. You get more and more complicated deformation modes. And now you're looking at the structure as an entire structure. And you look in the ways that the entire structure can deform. How much it can deform in each of these ways, that you don't know. But this is what you are about to solve. And you're about to solve that in a way that you're building the relationship between the nodal degrees of freedom and modal coordinates. Modal degrees of freedom, if you may. This relation is built by using this matrix here, which simply tells what are the ways that structure can deform. So it's not absolute values, but just the ways structure can deform. Now the beautiful thing is that this can have 10 units, 10 unknowns in the beginning, but this can just have like, let's say 2 or 3, and you don't lose that much in terms of accuracy. Maybe you don't lose at all, but maybe you lose just an insignificant number, if insignificant amount of accuracy, so you can live life. You can live well in your life. Okay, that's the concept behind it. So that's how it works. And we're going to rephrase and we're going to look at this many, many different times in today's lecture and the lectures that are about to come. All right, so that's it. Okay, let's look at shortly. If this was a static, things are not going to be that much different if I'm going to look at the dynamics. So if I would solve the dynamic responses here, so I would simply need to take the inertia forces into account like this. But I'm assuming that the force is not fluctuating that much as a function of time, so I can solve the static instead of dynamics. But if I wanted to find these vibration features, the features of the structure, then I have to take a look at this part of the equation, because dynamic features of the structure is all about how is a distribution of inertia and stiffness. And That's the way how you can solve the eigenvalue analysis too. So now I will shortly explain how is an eigenvalue analysis, very shortly, briefly. And then there's a next in-class quiz, which is about how many different modes, how many different ways structure can deform. And I can already tell you that, you know, if you have here a structure that there's a, let's say that there's no boundary condition at all. So there's a system that consists of 6 nodes. Each of these nodes has 2 degrees of freedom. So if there's no boundary condition, meaning that you're neglecting this connection to ground, this structure can deform in 12 different ways. 12 different ways. Where this is coming from is coming from this guy here. How many unknowns you have here in a vector of nodal coordinates. It's not related to how many elements you have, but it's only related to how many nodal degrees of freedom you have. Okay, that's going to be now my in-class quiz after, there's going to be one slide and then the in-class quiz. So put this in your mind. So if I'm asking that the structure that consists of, let's say, let's put it here like 5 elements, 6 nodal locations, and 12 nodal degrees of freedom. There's going to be 12 different ways that I can extract by using my eigenvalue analysis. 12, not related to number of elements, not really related to number of nodes itself, but the nodal degrees of freedom. Okay, so with that, let's take a look how is an eigenvalue analysis. Now comes something very important. So in eigenvalue analysis, I'm only figuring out the way structure can deform. So it's nothing whatsoever to do with the absolute displacement. How can I know that? I know that because in order to find out these eigenvalues and eigenvectors, I'm going to set the vector of external applied forces to be 0. So there is no forces involved other than internal forces, which are inertial forces and elastic forces. So those are the 2 forces that I'm looking at. So I'm kind of looking the balance between how is a mass distribution and how is a stiffness distribution. This is only information that I need because I'm looking at the ways or kind of the inherent features of the structure, nothing else. Nothing about how is the absolute displacement. So this is not related to that, but the way structure can deform. Okay. Now, if you're simplifying your equation of motion, it's just the way that you're setting these external applied forces to be equal to 0. Then, based on the mathematics, we know that the solution of the problem can be written like this. Now, let me read what I have in this solution. So I have here a vector, this one here. This was, by the way, was that what I wanted to draw before, but I couldn't make it that correctly. This was a, vector, how the structure can deform, and then there's a power I omega time. And once I substitute that information to this equation, I can read it like this. And what I have here is one way that the structure can deform, and then I have here something that is called eigenvalues. Eigenvalue will tell me what are the natural frequencies of the structure. This will tell me what are the associated deformation modes. So what I'm really after here is this guy here, this deformation mode. But as a side effect or side product would be the better way to say it, I'm also able to see what are the natural frequency associated to that particular way that the structure can deform. Okay, so how is that I can solve this way that the structure can deform? First thing that I need to do is that I need to solve this. Okay, so what first thing that I need to do is that I need to solve these eigenvalues. Okay, I'm gonna tell you what are these eigenvalues and eigenvectors with an example pretty soon. But I'm simply solving like what are the different values, eigenvalues that the structure can have. And if I have again, if I originally have here 10,000, not a degrees of freedom, this vector here will have a 10,000 different solutions, 10,000 eigenvalues, 10,000 eigenfrequencies as well. And then substituting one at a time these eigenvalues, this equation, I can find 10,000 ways that the structure can deform. This is in short how the eigenvalue analysis will go. And of course, you have no chances whatsoever to understand this based on my explanation. That's why there's going to be a numerical example momentarily that tells what exactly is this thing. But this time, I wanted you to learn this. If you have a structure which is modeled by using a finite element method, and in your finite element method, you have a 10,000 not a degrees of freedom. That means that there's a 10,000 natural frequencies in your system and 10,000 different ways structure can deform. That's what is that number is telling you. Okay. With that, I need to drink a little bit of coffee, and you need to think about what is the solution for this problem. So finite element model shown below consists of m number of elements and n number of degrees of freedom. Well, the better way to say this would be n number of nodal degrees of freedom. Model can be used to solve question mark number of eigenvalues. Question mark is equal than the elements, number of elements, equal than the number of nodal degrees of freedom, then element minus nodal degrees of freedom, element plus nodal degrees of freedom. And in-class quiz is on. Here. Okay. Okay, my slides are a little bit off, so let me correct them a bit. Oh, this is perfect. Okay, and the game is on. Well, how is the success rate? I got 3 answers so far, just 3. And the number of viewers is, that's record high, I think. It was 18 just a little while ago. 81. Oh, by the way, how was the success rate last time? I missed that completely. I need to check that. Because I did not announce the winner this time, and I'm not even sure if there was a winner. Okay. Anyways, now we have a new game, so let's play. The first case is 81, 77, 82. I'm thinking again 100. It's gonna be 100. Why? Because I know that you guys are all like outstanding students, and you're not actually watching YouTube or Winter Olympics while the lecture is on, but you're focusing my talks. At least this is how I wanted to explain it to myself. I don't know if that is the case, but this is the way that I'm explaining this to myself. Okay, and I got 10 answers so far. Last time I think that it was a 15 or 16. Don't remember that exactly. But think about it. 92, 72, 79, 81, 77. But no one except me is voting 100%. Where is your can-do attitude, people? And now we got the 19 viewers. So let's wait a couple minutes before we move on. And then we go back to this eigenvalue, natural frequency, and associated deformation mode. And we're going to play a little bit of videos to you. I think that most of you, this is pretty unclear, so pretty clear, so not much to learn, but still is not harm to refresh your mind. Okay. So I got 17 answers. 20 viewers, that's a record high number, so that's a bit surprising. Maybe I should get started a bit later, not get started at 8 o'clock, because 8 o'clock seems to be a little bit of a hard time for you guys, I guess. Okay, so I got 17 answers and no more is coming, so let me take a look how is a final success rate in the second in-class quiz of the day. So 17 and the number, okay, I just got the 18, so here it goes. 72. Okay, I have good news and bad news. Well, good news is this, that we got the clear winner. So we have a student that exactly hit the spot, exactly 72. So that was that student I recommend to do a lottery. So that was a good catch, good catch. So that's a good news. Bad news is this, I repeated quite many times that the only thing that matters here is a number of nodal degrees of freedom. So maybe you guys are still watching the Winter Olympics or something else, because what only matters is a nodal degrees of freedom. Number of elements doesn't really matter, and definitely is not related to how to subtract or adding these numbers together. They have no physical meaning whatsoever. They did have a physical interpretation, and it was the case in multi-body system dynamics. But remember, we are now in a finite time model, not in a multi-body system dynamics. Okay. Anyways, so let's continue then. Let me hide this one, and let's move on. Here. Okay, so what is this natural frequency? Well, the natural frequency is telling like what is a resonance frequency of the structure. Let's say that again. Well, let's make a simple example. So let's make a very, very simple example. That's the way that I have a mass and a spring, like this. And then I'm imposing the force that is mass. And the force is something that I'm measuring the displacement of the mass. The force is something that is fluctuating as a function of time, and I can vary the frequency of the force. And now when the force hits the frequency of the structure, the frequency of the structure is the one that is defined by stiffness and the mass here. When those two numbers are getting same, this response, this X response, is kind of getting out of the control. So it's getting out of the hand. Theoretically, now this is only theoretically, it behaves in such the way that this amplitude. So if this is how it behaves, these amplitudes, they go like infinity, and these how much they are increasing, that will follow the certain kind of mathematical rule. It's not typically the case. I mean that you cannot get the infinity, of course, but there is a certain limit how much you can do. But it started to behave like no limit. What that means? Behave like no limit. Let's take a look. Let's take a look. I have two videos here. The first one is playing, or is showing that what are the resonance conditions. So I have this similar kind of setup here. Let me see if this works. Yeah, it works. Let me make it a bit bigger. So I have platform that is moving left and right. And in the top of the platform, I have masses that are standing top of the structure that is a flexible structure. Let me see. It's thinking quite a bit. Okay, I want to take this voice off. Okay, so here's my setup. So I'm moving this platform left and right, and I'm keep on increasing the frequency of this motion left and right. So same amplitude, but the frequency will change. Now you see that this is not looking too weird at all. But soon I'm going to hit the first natural frequency. And the first natural frequency will be causing something quite surprising behavior. Now you see that the system in most of far right, it started to introduce quite a bit of motion left and right, the same direction where this motion was imposed. And you see that, let me see. Yeah, this hits the natural frequency soon. It's going to start vibrating like no limit whatsoever. Let me see. This is a little bit of slow video, but you see that this is the others are standing still because others have a different natural frequency. So they're not affected by the one where I'm hitting the same natural frequency. This was a 4 hertz. You see that the one in far right is going crazy, and I'm keep on increasing the frequency. It will calm down, and what you can obviously reckon, or what you're going to happen next, is that the middle one going crazy, and that's is then having this kind of weird, very large amplitude. So that's what the natural frequency is. That's the behavior of what you can introduce when you're hitting the natural frequency. So you get the resonance. That's what the resonance stands for. Okay, these systems can be simplified in such a way that I have 3 1 degrees of freedom systems standing, top of this moving plate. And what you're gonna, of course, what's gonna happen if I will jump to the very end of the video is this guy here, the one in the left, will go crazy. Okay, but this was the 1 degrees of freedom systems. Let me see if I can make this like this, a bit smaller. But what if I have more degrees of freedom? So let's take a look. What are what if I could have a system with a higher degrees of freedom? So now I have here a system that is a kind of simplified.
1 degree of freedom
Again, I don't want to hear this voice.
one natural frequency and one.
So if we could get started with a 1 degrees of freedom. So this again, the 1 degrees of freedom system. So there's one way that it can deform, and one way only. So if I have 2 degrees of freedom system, how many ways it can deform? Well, not the big surprise. 2 different ways. 2 different ways. Then the 3 degrees of freedom. This is the first way it can deform. And if we're proceeding in the video, there's going to be another way that it can deform. This was the first one. And here's the second. All right. 3 degrees of freedom, 3 ways. So on and so forth. Until if we go here, 4. This is the first way it can move. And soon it's going to be 3 other ways. All right, now then comes something interesting. This is the second. 2 to go. Third. And then finally the final 4th way. Oh, okay. Sorry, I misclicked something. So sorry about that. Okay. So something that I promised to be interesting is this. this is a structure that you guys are dealing with in your assignment. And when you look at the natural frequency of this structure, the lowest frequencies and associated deformation modes are something like this. This is a deformation mode ID. Where can I see ID 8? All right. First 6 are rigid body modes. Seventh would be the same kind of banana deformation, but this direction which here is a Z direction. So it will be out of the plane mode. Out of the plane mode. And now you see that the frequency here is at 51 hertz. All right. So this perhaps, or most probably, this is going to be something that when you're going to look at the structure where there's a hydraulic driven here and there's a mass in the end of this kind of beam-like structure, this kind of deformation modes for sure will play a significant role. Then there's an out of the plane deformation mode, which is ID number 9. This perhaps is not so important to you because your loading is not in this direction. So maybe you can skip this deformation mode. Maybe. There is, by the way, to find out which one you can actually skip and which one you have to keep in your simulation. And then you go moving ahead. This is a 10th. This perhaps again is important, but now the frequency is again getting to be a little bit high. So it's 147 hertz. But now you see what happens. You keep on computing these deformation modes. You get higher and higher frequency and more complicated deformation modes. And how much these super complicated deformation modes makes a difference to your structure? Not much. Their contribution is insignificant. Let's say that something that you don't lose much if you're ignoring them. Let's take a look at these really high frequencies. So this is a deformation mode, which is already 2,769 hertz. Yeah, maybe you still need this if you want to take a look at the really local deformation. But what about this one here? This is in 762 hertz. Yeah, again, if you want to take a look at the local deformation, this one here is 12,000, well, a little less than a 12,000 hertz. But wait a minute, 10,000 hertz and the deformation like this. How much is going to make your difference in your life? I don't think that it makes any difference whatsoever. Because look at the deformation mode. It's just very, very local deformation. Very local deformation where the single shaft is expanding. How is that you can introduce the force that can introduce this kind of deformation? Well, maybe by magnet or something, but it's going to be very hard to do that. So I don't think you lose much if you skip this deformation mode. That's exactly the idea in a modal reduction technique. Because if you have these 10,000 degrees of freedom, something I keep in repeating number of times in my lecture today, some of the deformation modes are very complex, very local, and they don't make much of a contribution to bigger picture. So maybe you can ignore them. And this is the way you can come down from 10,000 to, let's say, 100. Sometimes you can easily go down to 10. Sometimes it's enough to use just the 3 modes, 3 deformation modes. That's the idea in the modal reduction. Okay, here are the two different kind of structures. This is a paper roll, and then there is a deformation modes. Some of them are making a contribution to simulation. Some of them are just disabled. Just something that we are assuming they have no influence to behavior of this structure. This structure is kind of like rotating structure, and we wanted to see how it is its performance when we increasing the rotational speed. You see that all the modes so far are enabled, so they're part of the computing. Now the frequency is still well, now is a bit less than a 300 hertz. Everything is enabled. So let me make this a bit bigger so you can easily see this. Okay, still enabled 350 hertz, a little less than that. And this is going to be like expansion mode, still enabled. But soon there's going to be mode that are that are no longer are assumed to be significant, that they are ignored. A bit lengthy video. Here's the first one, disabled. This is disabled too. Why? Because we don't feel that this kind of deformation modes are playing an important role. Like I say, there is a rule to figure out which is important and which is less important. And you can set some threshold values to make sure that you only keep the important ones in the play. And we will need to get back to that next week. But this video is very lengthy. But you see that the frequency is increasing all the time, that the deformation mode in turn becomes to be increasingly complicated. And because they becomes to be increasingly complicated, maybe they don't play a significant role in the big picture anymore. They for sure are important in terms of very local deformation, but this time we are not interested in the local deformation, but the bigger picture, the big picture. All right, so the video is very lengthy, so let me take our result to this kind of deformation modes, which is now that the frequency is already more than a 1500 hertz. This is still labeled, so this is still part of the game. This is still part of the game. This is no longer in a computation. And now similar kind of animation for hydraulic cylinder or the piston rod of the hydraulic cylinder. Now the first 6 ones are rigid body modes, so they are disabled. And then one comes the more complicated from ID number 7. Then you see here if they are disabled or abled. This was the idea was to analyze the behavior of this particular rod. How it is behaving in certain kind of loading scenarios where there was anticipated that there's going to be a bending. So that's why the bending modes were all involved. More and more complicated modes. And if I'm gonna go here, these are now disabled because probably not important for us. Okay. All right. So let's take a look at let's go back to the mathematics then. How is this when we're moving from this nodal degrees of freedom to modal degrees of freedom? So if we're gonna take this conversion from nodal degrees of freedom to modal degrees of freedom. And let's say that this original is 10,000. And this is then just 100. Let's see what are the consequences. When you substitute that relation to this equation, now let me show you how it goes. So initially it's going to be like this. So it's going to be this deformation mode multiplied by modal acceleration, then the stiffness, like this, modal acceleration, and then let's just call the forces. Now the forces here are still expressed in terms of nodal coordinates, not in terms of modal coordinates. So to make this match, we have to multiply this by transpose of these modal coordinates. And what will be the consequence of that? So there's going to be this kind of expression. A little bit messy, but I'm sure you can still read this. Exactly like this one here. All right. Now, if these deformation modes are orthogonal, like they are, if they are based on eigenvalue analysis, then there is something super pleasant that comes along with this conversion from nodal to modal. And something super pleasant will be the fact that these degrees of freedom, modal degrees of freedom, are detached from each other. So they have no relation between each other. That can be seen when you do this multiplication. And when you look at how is a mass matrix that comes out from this mathematical operation, the mass matrix is identity matrix. And the stiffness matrix is the one that natural frequencies are located in a diagonal terms. meaning that these coordinates have no relation between each other. You can just take a coordinate ID number 100 and solve it without knowing anything whatsoever with the other coordinates. And that's a super pleasant thing, which is another booster for computational efficiency. So, modal reduction. What are the concepts? First of all, oh, maybe I can mention it in this slide here. So, modal reduction. What do you do with the modal reduction? You're moving from nodal space to modal space by figuring out what are the assumed deformation mode. And this deformation mode you can get from eigenvalue analysis. There are other ways to get it, and I will explain these other ways to you briefly. Maybe this week, or if not this week, then a week from now. And now when you're moving from modal, to nodal to modal coordinate. Sorry that these two words are so near to each other that sometimes it's hard to recognize what is what. So when you're moving from nodal to modal coordinates, then you can reduce the number of unknowns. So that's the first significant thing. Another significant thing is that you are no longer having the coordinates that are coupled together, but they're completely decoupled, so they're completely independent, which again helps to solve the problem. So two consequences. The first one is the most significant, and that's the possibility to reduce the number of unknowns. Second one is that it's mathematically more pleasant than original problem. That's another consequence. It's not so important than this that there's a possibility to reduce the number of unknowns, but still something that is worth to mention. Okay, so with that, let's take a look. Let's practice a little bit. And now, again, you see that there is this comment, which I learned that is some kind of virus thing. So make sure you don't click that link that is now in a chat window. Surprising thing. Okay, so I don't know what are the settings to get rid of this kind of comments, but doesn't really matter if we all know the name of the game. Right, so I'm going back to the spring element. Spring element because its computation is so pleasant. So I have a structure, spring structure. Oh, maybe it would be better to draw it like this. Spring structure like this. This is a structure in total. And I wanted to model this spring structure by using 3 elements. First, second, and third. So 3 elements like this. First, second, and third. And then I have here 1, 2, 3, 4 nodal locations. Each of these nodal locations has a 1 degrees of freedom only, because these nodal location can have only one way it can move, and that's going to be back and forth in y coordinate axis along the the x coordinate axis. Okay, so that's the setup here. Now, if I would build the stiffness matrix for the entire structure, I need to combine the matrices together. So here's where is my first and partly my second stiffness matrix is expressed. Here's where my second stiffness matrix is expressed. So it's influenced with the first and third. And here's where my third element is expressed. You know, this is this overlapping that I mentioned briefly earlier today to you. Now this is my entire stiffness matrix, and look at how many degrees of freedom. 4 degrees of freedom. So if I would conduct the eigenvalue analysis for this structure, I would get the 4 different ways that the structure can move, and 4 different natural frequencies. All right. Then here is my mass matrix. I'm using the same kind of matrix technique to describe the entire mass matrix of, entire structure. You see that the submatrices are associated to elements 1, 2, and 3. All right, so then first thing to do in my eigenvalue analysis, and this is, by the way, not the way these commercial finite element software are conducting the eigenvalue analysis, but that's okay. for sake of simplicity, I think. I'm not sure if this is simplicity, but just to make things clear, I'm going to first look at the determinant of this equation. And I'm setting this determinant to be equal to 0. Okay, first I'm going to take my stiffness matrix of the entire structure. Here it is. And then I multiply that by my eigenvalues. And now this is a bit confusing, I have to admit that, because I'm suddenly setting the notation to be lambda instead of this omega power 2. But don't get confused about that. Here's my unknowns. Those are the ones that I wanted to solve here. And then comes my stiffness matrix. So this, when you do this operation, lambda multiplied by mass matrix minus the stiffness matrix, this is going to be the matrix 4 by 4 in dimensions. And when you take a determinant out of that 4 by 4 matrix, this is how it looked like. And you see that this is a polynomial, which is a fourth order polynomial. I know that because, you know, the lambda is here, 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 and here. So 4 times multiplied by, so this is a fourth order polynomial. Fourth order polynomial has a 4 location where it goes equal to 0. And when I'm finding these places when it goes to 0, these are numerically shown here: 0, 12, 60, and 120. Okay. So now if, you know, this is, of course, keep in mind that this is a relation that I have used all the time. So my lambda is equal to then omega power 2. And from omega, you can go to hertz using this relation if you are looking for hertz. But again, let's just look at the numbers. What the first number is standing for us. Oh, I'm sorry. So what the first number is standing for us. Lambda equal to 0. Natural frequency equal to 0. That is rigid body motion. Because remember, in the structure we have no boundary condition here. So we're just sending these structures space, and we're looking how it behaves. What are these features in the space? So it's not attached to any of the boundaries. So it's just free to do whatever it wants. And the first thing that it will do is that it will have a rigid body translation. It will move like rigid body back and forth like this. Natural frequency associated to motion like that is 0. Second one is a motion, which I don't know how it looked like, but is associated to number 12. Okay. How is this motion? How is this deformation mode? That I can figure out next. And then there's also the one that is having the number 60, and I have then the one that is having the number 120. Okay, let's get started from 12. All right. So I'm substituting 12 to this equation. It gives me the matrix multiplied by the vector. Vector is my unknown, is the way structure can deform. Now keep in mind that this is just the way that the structure can deform, because this, don't know what this symbol, what is, I think it is phi, or anyways, this symbol here can be multiplied by any number you want. Any number you want, which is called scaling. It's called scaling. So if you want to multiply this number by 10, go ahead and do it. It's still going to solve the problem. I mean, it's still going to solve the equation. So it's not making any difference. That's why it's only telling you the relative motion. So if, let's say that if the structure originally like this, first deformation mode probably going to be something like this. So it's getting longer and shorter, like shown here. Oh, I'm missing one node. Like that. Now, if you would multiply this by 10, it would mean that this magnitude of deformation would be just 10 times bigger, nothing else. Way will be still same. Okay. Okay, here it is, you know, I have, when I do this mathematical operation, this one here, I got 4 equations, 4 unknowns, because this vector here consists of, excuse me, not enough coffee. So this vector here consists of 4 components, because the 4 degrees of freedom. Now 4 unknowns, 4 equations, and when I'm solving it, this is how it looks. So these are telling me the relative deformation. And again, it looked like this. So I have a structure originally list like this. The first one is moving -2, so it's going here. Second one is moving -1, going here. Third one, 1. Fourth one, 2. That's how it goes. Excuse me, so I could multiply this by this number by -2, or I don't know, minus 2. And then it will be completely different. So it will be, showing that this is a deformation way, extracting, constructing, getting bigger and shorter. This is how it is. What if I would compute the one that is related to frequency 120, or eigenvalue 120 more specifically? Then the deformation mode will be different, of course, and it's going to be like this. Okay, so if originally my structure is like this, so the first one is moving minus, going here. Second one, 1, minus, and then the 1. So it's like wave traveling within this structure. That's how it would look like. Okay, my next in class quiz. And remember, now, again, put Winter Olympics away and listen what I'm saying. The eigenvector, this vector here, is telling you numerically how is a deformation way. The way structure can deform, nothing else. Is definitely not anything related to like absolute values, nothing like that. Why I can tell you that? Because we computed this based on no forces, so there's no other forces than internal forces. So uh, inertial forces and elastic forces. So that's how I know it. Here comes my next in class quiz, and let me see what's the ID here. ID number 3. Let me see if we can go all the way to. Okay, I guess we cannot go all the way to number 5 today. But here's my in class quiz, and go ahead. Now, physical interpretation of an eigenvector. This one here. It's telling you a relative displacement on dotted degrees of freedom, absolute displacement on dotted degrees of freedom, strain distribution within the structure, no clear interpretation. You think about that, and I will think I'll drink a little bit of coffee. And I see we have a problem here. The problem is that it's already 9:40, so we only have 5 minutes left today's lecture. What I would like also to do today is that I would like to give you another streaming, which is about the carrier counseling. Carrier counseling ID number 2. This time the carrier counseling would be a little bit about how is a life in academia. So if you decided, or if your desire is to go to academia, what is the name of the game? So how it goes in academia, what are the important matters to take into account if you're looking for a career in universities? So while you're answering this question, so let me set up that streaming in the YouTube. So just a second. So I'm gonna schedule a streaming that will get started in 5 minutes. Okay, let's see how it goes, because I need to go live here. So Maybe he's not willing to do this while I'm still streaming. Yeah, I think I can do it. I can make it happen like that. Career counseling. Career counseling, second set. Public, and we're gonna get started today at 9:45 here. Okay, so it's set. So this career counseling is targeted for those ones that are thinking career in the universities. And now we're back here. So I can see that I have 14 answers. Let me take this one visible for us. 14 answers. So what is the correct answer? 15. So soon we're gonna, again, the problem in, maybe this is because I have another stream that will get started momentarily. But it complains that the quality is not very good at the moment. And the game is on. First case is 95. And I'm back in an excellent connection. Okay. Oh, exactly two same numbers, 87. Mine is still this. Still 100%. Okay, I got 17 answers. I think that I need to go because I only have 2 minutes before the next streaming will get started. So, and you can see the streaming, I mean, the link for the next streaming by going to Core's YouTube's channel. And it's scheduled to get started at 8:45. So after 2 minutes, less than 2 minutes. Okay, so with that, let's take a look. 84. Well, 94. That's a really good. That's a really good. That's a really good. You know, we're getting close to this 100%, and I somehow thinking it will happen in this class. And not just a single time, but the number of times, multiple times perhaps. Okay, so 94. Now let me take this away. There's going to be quite a bit of other things to discuss, but we will continue a week from now. And I'm going to close this streaming. Take yourself back to the core YouTube site and see me momentarily regarding the career counseling related to how is it a life in academia. All right. So, and then those of you that are not coming to see my career counseling, I will see you on Monday then. Monday at 8:40, 8:15. See you next time.